You know, from the fizz in your soda to the battery that's powering your phone, our world is just in this constant state of change. And behind it all, there's this hidden script, and that script is chemistry. So today, we're going to put together a kind of field guide to its most fundamental language, chemical reactions.
All right, let's start off with a little bit of a puzzle. What could possibly connect the amazing smell and transformation of batter into a cake with the slow, silent decay of an iron nail that's been left out in the rain? I mean, you'd think they have nothing in common, right? But believe it or not, they are both perfect examples of the exact same fundamental process. So before we can go out and be chemical detectives, we really need to know what we're looking for. And the first step? Well, it's knowing that not all changes are the same. We have to be able to tell the difference between two really key types. Okay, so on one side, you've got a physical change. Just think about ice melting into water. Sure, it looks different, but chemically, it's still H2O. No new bonds were made. But a chemical reaction, that's a complete makeover. The stuff you started with breaks its old bonds, forms brand new ones, and creates something entirely different.
So here's the bottom line. In any chemical reaction, you start with your ingredients, we call those reactants, and you end up with your final dish, which we call the products. The reactants literally get used up to create something new. That's the core idea right there.
Okay, so we've got the what, but how do you actually see one happening? The good news is, you don't need a super powerful microscope or anything. You just need to know the clues. Think of yourself as a chemical detective, and you're out there looking for evidence.
And here's your checklist. When you're looking at something, ask yourself, is there a weird, unexpected change in state, like a liquid suddenly forming a solid? Does the color just completely change? Are you seeing bubbles of gas appearing out of nowhere? Or do you feel it gets suddenly hotter or colder? Any of those is a huge sign that a chemical reaction is going down.
Take burning magnesium, for instance. Wow. This one checks almost all the boxes at once. The solid metal ribbon turns into this fluffy white powder. That's a change in both state and color. And it gives off this incredibly intense light and heat, a massive change in temperature. It is a textbook, no doubt about it, chemical reaction.
All right, detective, you're getting good at this. You can now spot a reaction. The next level, the next step in our field guide, is to figure out what type of reaction you're looking at. And the cool thing is, most of what you'll see falls into one of four main categories. So let's break them down. First up, we've got the combination reaction. And this one is super easy to get. It's literally like baking. You take a bunch of simple ingredients, your flour, sugar, eggs, and you combine them to make one single more complex thing, the cake. Two or more things become one.
And here's a classic chemical example of that. You take some calcium oxide, which is also just called lime, and you add water to it. They combine, and you're left with just one new product, calcium hydroxide, or slaked lime. Simple as that.
Next up, we have the total opposite, decomposition. So if combination is about building something up, decomposition is all about breaking it down. Imagine a big, complex building just crumbling down into a pile of simpler bricks and dust and beams. One thing becomes two or more simpler things.
Now, this kind of breakdown doesn't just happen randomly. It needs a little push, an input of energy. And that energy can come in a few different flavors. You can use heat, you can use light, or you can even use electricity to kickstart the process and break a compound apart.
Okay, our third type is the displacement reaction. And this one's fun. I always think of it like a chemical dance-off. You've got a couple dancing together on the floor, that's your compound. Then a more energetic, more reactive dancer comes along, cuts in, and steals the partner, leaving the other dancer all alone. So check this out. In this equation, you can see copper is dancing with sulfate. But here comes iron, who's way more reactive, so it just swoops right in, kicks the copper out, and forms a new partnership with the sulfate. And the poor, less reactive copper, it gets left all by itself. It's a classic chemical partner swap.
And our fourth main type is the precipitation reaction. Honestly, this one can look like a straight-up magic trick. You take two totally clear liquids, you mix them together, and then all of a sudden, poof, a solid material just appears out of nowhere, almost like dust, and it drifts down to the bottom. So, you take a solution of silver nitrate and another of sodium chloride. They're both basically just clear liquids, like salty water, right? But when you mix them, they react to form solid silver chloride. That solid stuff is the precipitate. Since it can't dissolve in the water, it just appears as a solid and drops out of the solution. Okay,
We've made it through the core four, but there's one more big one we've got to talk about. Think of it as the final boss of reaction types, the redox reaction. It's a little more complex, but it is happening constantly, all around us.
Redox is actually short for reduction oxidation. And here's the key thing to remember. They are two sides of the exact same coin. You literally cannot have one without the other. In the simplest terms, oxidation is when something gains oxygen, and reduction is when something loses oxygen. They're a perfect pair, this constant give and take.
Let's trace the oxygen in this reaction here. The copper oxide, it starts with an oxygen atom, right? But it gives it away, and it ends up as pure copper. Since it lost the oxygen, we say it was reduced. So where'd the oxygen go? Well, the hydrogen grabbed it, forming water. Since it gained the oxygen, it was oxidized. See, it's a perfect transfer. One gives, the other takes.
Okay, so that was a lot of theory. And you might be asking, so what? Why do I need to know all this? Well, this is where it all comes together. It turns out these reactions aren't just things that happen in a lab. They are the engine that runs our entire world. Just think about it for a second. Combination reactions, they're building the very stuff you're made of right now. Decomposition reactions, they are hard at work digesting your last meal to give you energy. The battery in your phone, that's powered by a displacement reaction. And redox, oh man, that's almost everything else, from a rusting nail to a car engine to the very air you're breathing in and out.
So there you have it, your very own field guide to the language of chemistry. You can tell the difference between a physical and a chemical change, you know the clues to look for, and you can even start to classify the reactions you see. The world around you is just one big, amazing laboratory. So the only question left is, what reaction are you going to spot next?